Hey everyone, my name is Neha Sivakumar, and in this video I'll be presenting my results from Lab 3, which focuses on a macroscopic view of DC and RC circuits. Quick overview. These are the topics I'll cover in this video. These include an introduction to the lab's purpose and methods, explanation of physical principles, observations from the experiment, and some reflective Q&A. In essence, the purpose of this experiment was to use the principles of energy and current conservation to predict the behavior of circuits containing resistors in series and parallel, use multimeters to measure the actual values of conventional current and potential differences in the circuits, and examine the behavior of ohmic resistors and capacitors. To perform this experiment, I had to use the Circuit Construction Kit, CCK, from the Colorado PHYS project to explore time-dependent voltage and current in DC and RC circuits. During the experiment, I simulated different manipulations to circuits according to the lab instructions. The 4 laws shown on this slide were foundational to the lab. Loop rule states that the sum of all electric potential differences around a loop equals 0. Node rule states that the sum of currents flowing into a node and into an electric circuit equal the sum of currents flowing out of it. Ohm's law states that the voltage drop across a resistor is proportional to the current flowing through it and its resistance, and the theory of capacitance gives the formula shown on the slide. Additionally, in Section B of this lab, the ideas of resistor equivalence and RC circuit charging were important. Now onto the details of Section A, where the lab focused on charge and energy conservation in series circuits. Given the circuit setup, I was asked to predict the currents I1 and I2 that would be measured by the 2 ammeters. Through some calculations, I was able to predict that the current would equal 0.02 amps. Once I recreated the given circuit setup in CCK, I found that the ammeters read I1 and I2 equal 0.02 amps, rendering my prediction accurate. When the ammeter is inserted backwards, it still reads that I1 and I2 equal 0.02 amps. When I replaced one ammeter with 1 voltmeter, the ammeter shows that I equals 0 amps, which makes sense since the circuit is open and there is no current flow. On the other hand, the voltmeter shows that the potential difference equals 3 volts, which also makes sense since the voltmeter only reads potential difference across the battery and potential difference equals 0 since the loop isn't complete. When asked to remove the voltmeter and close the circuit, and then use the voltmeter to measure the potential difference for each part of the path around the circuit, I found that the potential difference of the battery equals 3 volts, potential difference at the 47 ohm resistor equals negative 0.959 volts, and the potential difference at the 100 ohm resistor equals negative 2.041 volts. The sum of the potential differences for a round trip around the circuit should be 0 volts, so using the information I just found, I calculated the sum and found that it was in fact 0 volts. Here's a look at the diagram that shows the potential difference at different points in the circuit. The battery raises the potential, while the wire does not change it since it is considered to be ideal and without resistance. The resistors decrease the potential, hence why potential difference at the 47 and 100 ohm resistors were negative in the last slide. And the ammeter doesn't change the potential since it is also considered ideal. When I attached the voltmeter to the circuit, the ammeter reading didn't change because the voltmeter has such high resistance that little current can flow through it. The current flow in the rest of the circuit is almost negligible. If the ammeter is connected with a 100 ohm resistor, both the ammeters will read 0.06 amps, as the calculations shown above. When I replace the voltmeter with an ammeter in parallel with the 100 ohm resistor, the current through the ammeter becomes split between itself and the resistor. This happens because the ammeter has 0 ohms of resistance. Therefore, the current takes the path of least resistance and encounters only the 47 ohm resistance, not the 100 ohm resistance. Now, to calculate the resistance of each of the given circuit elements, I used Ohm's law as well as the formula R equals delta V divided by I, and found that the values listed on the slide. Here I showed which values of delta V and I were used to perform the calculations. Now, onto the details of Section B, where the lab focused on experimenting with RC circuits. When I connected batteries to the 10 ohm bulb, the light started off bright, then dimmed down. When I did this, the current in the circuit decreased as charge built on the capacitor. When I disconnected the battery and connected the capacitor directly to the 10 ohm bulb, the light did the same thing as last time and dimmed down after starting off bright. In this situation, where the battery was removed from the current circuit and the capacitor began discharging, the current decreased as the capacitor discharged. During the simulation, I measured how long it takes for the capacitor to charge and discharge using the 10 ohm and 20 ohm bulbs. In doing this, I found the time values shown on the left, but the important thing to note is the connection between the charge and discharge values between 10 and 20 ohm bulbs. Since the 20 ohm bulb has twice the resistance of the 10 ohm bulb, it makes sense that the time to discharge and charge at this doubled resistance is also doubled, and this result was exactly as expected. For part 2 of this section of the lab, I had to run a new procedure to explore time-dependent voltage across a discharging capacitor. Listed on the slide is the procedure I followed, and to the right is a diagram that outlines the setup for this type of circuit. To estimate the RC value graphically, I used the loop rule to solve a differential equation that helped me find that delta V equals delta V naught times e raised to the negative t over RC. From here, I had to linearize the equation to better suit my data and found that the slope of my linearized data is negative 1 over RC. From there, it was simple to find that RC equals 6.906 seconds experimentally, and I compared that to the theoretical value of RC, which is 6 seconds, which means that the value that I found was relatively close to the theory. The first challenge question asks, if I were doing this lab in real life and used an actual ammeter instead of an ideal simulated ammeter, what's the difference about a real ammeter and how would it have affected the circuits that I hooked up to it? And I answered that the ideal simulated ammeter makes it seem like there is 0 resistance caused by the device, but in reality the ammeter would have some amount of resistance. Because there would be this resistance that is unaccounted for in the ideal simulation, the amount of current in the circuit would be less. This agrees with Ohm's law since current is inversely proportional to equivalent resistance. In the second challenge question, I was asked about the charging time in real life if using a real battery to charge a real capacitor. And for that, I answered that in this situation, the capacitor would charge instantly. The capacitor would need little to no time, almost near 0 seconds, to reach full charge. This is because in real life settings, all circuit components have some resistance that must be taken into account. Well, that's all for this lab. Thank you for listening, and see you in the next video.